moles of hydrogen react with 1 mole of oxygen to give us 2 moles of steam. Steam is also a gas, oxygen is a gas, hydrogen is a gas. Okay, so we are required to calculate the volume composition of the resulting mixture. Go back to your, look at the volume here. 2 volumes of hydrogen react with 1 volume of oxygen to give us 2 volumes of water. So if I have 100 of this, from our ratio of 2 to 1, if I have 100 of hydrogen, that means the amount of oxygen that can react will be half of 100, which is 50. However, how much do I have of oxygen? I have only 30. Okay, so implying therefore that not all the 100 will react. It's how we reason easily. But however, if I have all the 30 of oxygen reacting, then that of hydrogen must be 2 times 30. When I multiply 2 times 30, I will get 60. So that means I will have 60 of hydrogen reacting, then I will have 30 of this one reacting. And out of 100, if 60 has reacted, that means the remaining will be 100 minus the 60, which will be 40. Then how much of steam will be formed? Since I have 2 of hydrogen forming 2 of water, so if this one, what is reacting here is 60, then that means even steam will be 60. That is why now in our calculation we are saying the volume of the mixture now is going to be the volume of the unreacted hydrogen gas plus the volume of steam formed. What is the volume of the unreacted hydrogen gas? It will now be, okay, you see, very simple, it will now be 100 minus the 60 giving us 40. What will be the volume of the steam formed? 60. Therefore total volume 40 plus 60 giving us 100. You see how simple it is, but it is based on your correct equation. That is how simple it is. Let's go to the second law. Okay, let's go to the second gas law, Boyle's law. I know we shall look at this majorly in physics, but we can mention, okay, Boyle's law is about proportionality. So this one says that the volume of a given mass of a gas is inversely proportional to its pressure at a constant temperature. The volume of a given mass of a gas is inversely proportional to its pressure at a constant temperature. We can illustrate this. Volume, which you can represent with V, so we are saying it is inversely proportional to pressure, which we are representing with P. Therefore, what does this mean? It means since the proportionality is inverse, if we increase the volume of a gas, the pressure reduces. If we increase the volume of the pressure, the volume reduces. So they are inversely proportional. As one is much, the other is low. Okay? So therefore, if we introduce our proportionality constant, which is kappa, or some of you will say K, but that letter there is kappa. That we are saying therefore that the volume is inversely proportional to P. If where K is the constant of proportionality, and from what we have explained, it means that when the pressure is increased, the volume of the gas decreases. Likewise, when the pressure is decreased, the volume of the gas increases. As simple as that. Okay. Can we now assuming the volume, okay, assuming V1 is the volume of the gas measured at pressure P1. This volume V1 can be converted to volume V2 at another pressure, say P2, provided the temperature of the system is kept constant. And that is why now using this formula here, we can have P1 times V1 is equal to P2 times V2. Okay, and from there we can be given therefore work to do. We can be given pressure 1, volume 1, and given say pressure 2, and you're told to determine volume 2. So using that formula above, we can now be able to work out. Let's look at the third law, Charles's law. It is also about proportionality. This law states that the volume of a given mass of a gas is directly proportional to the absolute temperature, provided the pressure is kept constant. Okay, so there's a direct proportion here. It states that the volume of a given mass of a gas is directly proportional to the absolute temperature, provided the pressure is kept constant. Okay, and that's what we are saying. So therefore representing volume with V and temperature with T, so we are saying volume is directly proportional to the temperature. And if we introduce our constant of proportionality, we shall therefore have volume is equal to kappa times T. Or we can make the proportionality constant the subject, therefore we shall have the constant given by volume divided by the temperature. where the temperature, okay, I mean where kappa is a constant of proportionality. Okay. This means that if the volume of a gas is doubled, the temperature also doubles, provided the pressure is constant. Now, assuming V1 is the volume measured at temperature T1, this volume can be converted to volume 2 at another absolute temperature T2. And that is why we can have now V1 over T1 is equal to V2 over T2. Okay? And because of this, therefore, we can be given V1, given T1, given V2, and told to determine T2. Or given T2, given V2, given T1, and told to determine V1. Okay? That's how simple it is. Okay? Now we can combine Charles' law and Boyle's law, and we get what we could refer to as the ideal gas equation, which will now be P1 V1 over T1 is equal to P2 V2 over T2. Okay? Standard temperature and pressure is what we want to look at now. The standard temperature and pressure, okay, are always chosen as 0, or we can say this is equal to 273 Kelvin. And what is the standard pressure? 760 millimeters of mercury, which is also equal to 1 atmosphere, or which is equal to 101,325 pascals. Pascals can also be referred to as newtons per meter squared. So the units are the same. 1 pascal is equal to 1 newton per meter squared. Okay, so this will be given to you, please. This will be given to you, but take note, the standard temperature and pressure is 0. Okay, I mean the temperature is 0, and this 0 degrees Celsius is also equal to 273 Kelvin. The pressure, okay, is 760 millimeters of mercury, and this is also equivalent to 1 atmosphere, or equivalent to 101,325 pascals. And we have said, okay, 1 pascal is equal to 1 newton per meter square. That means we can also say this is equal to 101,325 newtons per meter squared. Okay, therefore the standard temperature and pressure, okay, since we're saying are chosen as 0, okay, or pressure of 760, okay, so we can now use that to calculate, okay, whichever number that we are given. Let's look at an example 1. We are saying a certain mass of a gas occupies this volume, at which temperature 18 degrees Celsius and pressure 740 millimeters of mercury. What volume will this gas occupy at 20 degrees Celsius and the pressure of this? We go back to our, okay, so here there from our solution, our P1 is 740 millimeters of mercury, our V1 is, okay, 211 centimeters cubed, our T1 is 18, okay, which is equivalent to 291 Kelvin, okay, by adding 273 to 18. Okay, our pressure 2 is 770 millimeters of mercury. Volume 2 is what we want to get. Temperature 2 we are told is 20, which is equivalent to 293 Kelvin. And therefore, by applying the ideal gas law, okay, which was P1 times V1 over T1 being equal to P2 times V2 over T2. So by substituting, therefore, if we substitute 740 times 211 out of 291, which is equal to P2, which we are told is 770, V2, which we want, and T2, which we were given as 293, and therefore V2 therefore will be 204 centimeters cubed. Okay, as simple as that. Look at example 2. A certain mass of a gas occupies this volume here. Temperature this, pressure 7380. They are saying calculate the volume of this gas at STP. What is our P1? 738. Okay. What is our V1? 146. What is our T1? 18 degrees Celsius, which is the same as 291 Kelvin. What is standard pressure? 760 millimeters of mercury. What is our volume 2? We don't know. What is standard temperature? 273. So therefore, again, by applying the ideal gas law, we can now P1 times V1 out of T1 is equal to P2 times V2 out of T2. And in so doing, therefore, when we substitute, we shall have 738 times 146 out of 291, which is equal to P2, which is 760, times V2, which we want, out of T2, which is 273, and therefore our V2 will be 370.3 centimeters cubed. Example 3. We are told a certain gas occupied 360 centimeters cubed at 0 degrees Celsius and 700 millimeters of mercury. Determine the volume of the gas at STP. I think this one you can even work out easily. So what is our P1? 700 millimeters of mercury. What is our V1? 360 centimeters cubed. What is our T1? 50 degrees Celsius, which gives us, so when we add 273 to 50, it gives us 323 Kelvin. What is our P2? 760, since this is the standard pressure. What is our V2? Is what we want. What is our T2? 273. This is the standard temperature, since they are saying STP. So again, applying the ideal gas equation, P1 times V1 out of T1 is equal to P2 times V2 out of T2. And in so doing, when we substitute, we shall have 700 times 360 divided by 323, which is equal to our P2, which is 360 times V2, which we want, out of 273, and therefore our V2 will be that. Okay, very easy. So can we look at therefore, okay, having understood standard temperature, standard pressure, okay, now we come to calculations of gas volumes from equations. Okay, however, this can only be done if we have written the correct equation. Okay, let's look at what we call the molar gas volume. What is molar gas volume? Okay, even just by looking at molar, okay, molar gas volume. So this refers to the volume occupied by 1 mole of a gas at standard temperature and pressure. The molar gas volume is the volume occupied by 1 mole. This should be our emphasis, 1 mole. So meaning therefore, the molar gas volume will contain 1 mole of that gas. Okay, so this volume is a standard and will be given to you. This volume can be 22.4 liters. Okay, but remember 1 liter is equivalent to 1 decimeter cubed. That means we can also say it is also equivalent to 22.4 decimeters cubed. Okay, however, 1 liter is equivalent to 1000 cubic centimeters. That is why we are saying the molar gas volume can also be 22, okay, 40 centimeters cubed. Okay, take note of that. Okay, this is true for all gases as long as the mole is considered. Okay, 1 mole of oxygen therefore occupies 22.4 liters. 1 mole of nitrogen gas occupies that. 1 mole of carbon dioxide occupies, okay, the same. 1 mole of chlorine occupies 22. So it is just a matter of, so 1 mole of every gas will occupy the same volume. Okay, and based on that, therefore,